these three last presentations are supposed to be very fast, quick talks, and the idea was to do it in pecha-kucha style, the Japanese word for chit-chat, basically. 20 slides, 20 seconds each. So it's going to be very, very fast. Let's start.
Not mine, but...
Okay. Let's see if this works. It's a really good start.
That's your first light on.
It's a really good... okay. So, okay. Already last 8 seconds. The future of virtual reality. My idea here is to give you a sort of view of what is in the pipeline, what's to come. By the way, this is a very nice illustration that illustrates how I see about virtual reality. I mean, it's the dystopic side and the very nice vision side. So, okay, where are we now? No, where were we 50 years ago? We were in the lab phase, big, expensive computers. People were lining up to come here. It was a bit the same with VR labs in the 90s. People were lining up to use the lab's big, expensive facilities. Then, not so long ago, we entered the home phase. People actually buy VR stuff, putting in their homes, stuff you have tried today. Can be compared to the home computer boom during the 80s, the Commodore 64 and the happy mother teaching her kids to program and so on. Perfect. Now, what will we have in front of us is the ubiquitous phase, you could call it. Smartphones and tablets and such, wearables, we're here now. But when it comes to VR and AR, I think in future we will enter some sort of ubiquitous phase where we have this technology all around us. I haven't practiced, actually. So if we look at this hype cycle by the American analysis company Gartner, you see virtual reality is here, and the less-known cousin augmented reality is also slowly climbing this curve to the plateau of productivity, where this technology is actually part of all our lives. And if we look at the so-called form factor, here we are right now. It's big, clumsy cables everywhere, not so beautiful to look at. Hopefully, in a couple of years, we will be here. It looks more like a pair of big ski glasses. And then jump 7 years more into the future. Hopefully, everything will be rendered in the cloud with 5G connections or 6 or 7G connections and so on. Okay, display technology. We're here now. We're sending, we're showing stuff on screens, running it through optics, and get a nice little image here on the retina. Well, why not shoot the light straight into the eye with a sort of raster technology? We'll call it sort of virtual retinal display, it's called. That's probably part of the future. Now I start to feel I'm losing control here. As you can see, getting slightly nervous. Okay, pictorial realism. That was supposed to be a movie, it doesn't work anyway. So we can simulate in real time with game engines, like Unreal Engine 4, for example, stuff that actually look photorealistic. And this, of course, is not going to get worse in the future. It's just going to be better and better and better. How about locomotion? Well, this is today the best you can produce when it comes to moving in a virtual environment. This is a military-grade system produced by a Swedish company, actually. Cost a shitload of money. Nevertheless, we want one, or 2, or 3. And it's very interesting to follow how this kind of technology is going to change with time. How about simulating touch, actually touching stuff? Well, 2 interesting technologies here. First, microfluidics, which has a long history, for example, within inkjet printers, invented here in Lund, I believe, and ultrasound. And some crazy people actually think this is the future. If you've seen Ready Player One, some of you on the cinema, this is more like what it is there. I saw it with Oscar, great film. See it or read a book, even better. Spatial sound. This is crazy. Actually, today, if you tried the HoloLens, maybe you noticed that the spatial sound is really good. And that's a kind of simple sound localization with something called heterolytic transfer function. This is going to get huge. And simulating the environment's effect on the sound is going to get even better with frameworks like NVIDIA VRWorks that are actually available as we're speaking. And of course, I don't think this will work either, unless I do like this. Okay, maybe now it will. Okay. Okay, let's see if I can. Okay, just showing you a little bit of.
Well, the curtains absorb sound and dampen acoustic effects. The second floor by comparison, is more open, but composed almost entirely of hard surfaces which reflect sound well. As we head to the top of the atrium, we hear the decreased size of the surrounding space just as much as we see it. If we leave the atrium entirely, information carried along the auditory channel makes it clear that we've left the enclosed space of the atrium.
So that's an example of how you can simulate in real time different sound environments. And this is very new, and it's going to get very, very applied in the future, I think. Okay, olfactory displays. So you can see, you can touch, you can hear stuff. Can you actually smell it also? Yes, according to some people. This is one product that has been trying to get money through a Kickstarter project. I don't know how it went, but the idea is to simulate smell, heat, the wind in the face, and such. Eye tracking is also going to get huge, and we have a real expert here, not a happy amateur like myself. And for example, here we can imagine we know where the user is watching, then we could render just that in high detail, and then render with less detail the further out you come. It's called foveated rendering, and it's already becoming something to think of. And like I said before, why do we have to have these big clunky things on our heads connected to even clunkier computers? Why not have something really small and beautiful and made by some Italian designer that have a 5G connection and just let the cloud handle all the rendering and all that boring stuff? Social VR. Actually, today it's possible. If you try the Oculus Go, you can watch World Cup together with all your friends, hang out in Facebook. So this is not the future, this is now. People are actually sitting inside watching football together and having a great time. So this is going to get huge, grow a lot, and we have different platforms for this. Yes. So we talked a bit about web-based VR before. This is an example from web VR. You see a film on a homepage, you click it, and you get directly sent to the VR version of that film clip. So the web and VR like melts together in a very nice way. So what about the distant future? Well, if you ask this guy, Elon Musk, he really thinks that one day we will be able to simulate realities that are so real we can't differentiate them from real reality. So he basically says, 40 years ago we had Pong. What will we have in another 40 years, given that today we can simulate really, really nice stuff? Thank you for listening. Okay.
Will you do that again?
It was quite fun, actually. So I think so. Okay, now it's you? Okay.
So, hello everybody. I'm Florent Renaud. I work in astrophysics. A lot with Oscar. So I will show you stuff that you will connect to what he has shown. Which is basically in the topic of visualizing the universe. So actually what I'm going to tell you today is kind of a story of what happened to me in the last few months and how I do this kind of research, which was a bit new for me. So what you are seeing here is an object that we have studied with collaborators. And it's basically this type of object. I will give you a little bit of context very, very quickly. These are ring galaxies. They are kind of rare, so maybe it's the first one that you see. But they're quite nice because they have quite simple geometries. So we can use them to test the theories on star formation, for example, on many things. So how do they form? They result from an impact between a disk galaxy and a small intruder going through that. And what you are seeing here, the ring, do we have a pointer or something? The ring that you're seeing here is basically a density wave which is expanding radially. Thank you. So that's the result of this. And with telescopes, with combining different telescopes, different wavelengths, we can arrive at a multidimensional visualization of this object in the universe. And already with that, we can learn a lot about star formation and about a lot of physical process going on there. But if you want to understand a bit more, for example, time evolutions, you need to do numerical simulations. And this is not the simulation we did last year. It was much, much earlier. It was very simplistic, visualization was clearly not priority at this time. But it was very helpful to understand the process that if you have this tiny companion going through this disk-like object, then you get this expanding density wave. So you understand the physics from here. Many years later, we have much more powerful computers. We have more implementation of the physical process that we understood. And this is what we are doing. So here you see this disk face on. The companion is in your direction, is flying, going through. You don't see the companion. I don't show it, but it's there. And you see the density ring expanding. So with this little movie, which, believe it or not, is quite already cool for us and to show in conferences, for example, because you see where the stars are, where the gas is, etc. We can already learn some things. But then I use a new tool developed in Marseille by a very nice guy, Jean-Charles Lambert. So this tool is called GLNemo 2. And you can actually load your simulations and render whatever you want. And one very, very nice thing is that you can move the camera. So I took a static view of my simulation, and I moved the camera. I can rotate, I can zoom. There are still a few limitations, but the nice thing is that I can drop an email to the developer, and I can get a new version basically the same day. It's very, very productive. And the one cool thing that we discovered that if you look from edge on, you have a very thick distribution. It's not just a thin ring, as we could guess from observations and from previous simulations, but we actually have a thickness there. So the ring structure is actually a cylinder. And we never thought of looking at that before, so this was the first time we see that. So of course we thought maybe it's a numerical artifact. So thinking through, we say what could cause this numerical artifact where there is no particular reason, so let's try to compare it with the reality with observations. So that's again the simulation. The main ring is this structure here to see edge on, and you see the cylinder there. If you go back face on, this corresponds to this. So this is something a lot of people have seen before, and you have the main ring, which is this fluffy, fuzzy structure there. And if you look closely, you have this dense, very narrow structure here, goes around, which is the top of the cylinder. They are just in projection in this view. And so we thought maybe this exists in the real universe. So we went to another galaxy, this one, real one, and we looked closely, and these have been known for decades. And we looked very closely, and I think that we identified the main ring and the top of the cylinder there. So I will make it blink several times so that you can actually match. And I think we have these two structures there. So the point of this kind of analysis and of this little story is that now we are going back to the telescopes. And we are asking for time, then we get new observational data. So from this galaxy, we get these completely new observations. They are a bit rough. They are not very, they are not analyzed at all. We just got that a few weeks ago. And we have here full data cubes. So for every pixel in this map, we actually have the full spectrum in all wavelengths. So we can do a lot of diagnostics and learn a lot about the physics. And even because of this, that we only got a few weeks ago, we already have triggered a new phase of new observations to learn a bit more about, for example, this structure that we don't really know what it is, and others. So in the end, if I want to generate that, the starting point of our kind of research with Oscar is more or less always observations that triggers simulations, and then we put some visualizations tool in order to help us interpret the results, to build up theories, and then these theories need to be tested against observations. So we have kind of a loop here, where actually the observations will lead to discoveries, the interpretation as theory will lead to understanding of the actual physics and the universe, and in visualizations, what we have is basically cool movies for showing off in conferences and outreach events. And when I mean showing off in conferences in a kind of funny way, what I actually mean is keeping your audience awake. And when you have a week of talks, keeping your audience awake is very important if you want to share your results and if you want your insight to be more known. So now if I go to this type of plot, so it's the end enjoyment from Oscar, but from my perspective and the evolution of time, I would say that I start with a lot of excitement. My stress level is more or less constant. My distance to coffee is very close, very small, and always constant. I start with a lot of excitement when we have observations, and then a bit of stress, because I have to make the simulations, and the code crashes, and I have to restart and everything. And then I get results, so I'm even more excited. I make a visualization, then I don't understand anything, and then I'm back to observations. But the key point is that the end of this loop, even if it's a cycle, it's much higher than the beginning, so it's always more and more excitement when you're doing that. Thank you.
And then you go on holiday. Cool down. Yes. Right, so I'm Diederik Njorster from the Lund University Humanities Lab. Just call me D, it's much easier. And I'll tell you a bit about eye tracking, and I'll try to hurry up. As I'm actually Dutch, this is a beautiful building of the main I'm going too fast. This is a beautiful picture of the main building of Utrecht University. And the main point I want to make here is, like, as you look around the world, you feel like you're seeing everything, right? But what you're actually seeing, if you look at a specific point, is more something like this. You're seeing sharp and clear and focused where you're actually looking, and your resolution quickly drops off to the side. You can all see that, right? When I look at your face, I can't see any other face clearly, actually. You all know that if you think about it for a second. So that's why we make eye movements. We need to look around to kind of stitch together the world, so to say, in a clear, coherent picture. So how do you, so that's very interesting to study, right? Because it's kind of the input that we get. So then we use eye trackers to measure how that works. They work like this. I don't know who this is, but doesn't look very nice. Actually, the first eye trackers kind of worked like this. They were a plaster cup that you put in your eye, had some cocaine so you don't feel anything, and you're all good. 100 years ago, they used cocaine for pain killing, right? But anyway. Anyway, so we have machines that we can measure what you look at. It's a useful tool for studying. So I'll give you one tiny example of what you can do with that. This is actually a really long time ago. I worked in a marketing company. So we did stuff like this. We had people read a fake magazine. So we had an article here with text and advertisement. Of course, we got paid to test these advertisements. And I'm showing you here with this red dot where a person is looking. And your task is to figure out what is it that attracts their attention. So what do you get from this video? What is it that people look at? Anyone? Yeah, of course you're allowed. Faces. Very good, faces. Faces are real attention magnets. We're social animals, right? But a different question. If you paid a lot of money for the advertisement, are you happy now? No? Why not?
Looking at the product.
Indeed. I mean, maybe people felt a bit happy with all these smiley faces, right? But they didn't see your brand all the way in the corner there. They didn't see your message. They didn't look at any of that, right? And of course, you can wonder, like, yeah, they didn't look at it directly. Maybe they still could see it and process it, right? But just try for yourself. Look at that where the red dot is now. Can you see the logo? Can you read that? No, right? So you know for a fact that it's just not possible to process that if you're so far away. So that's why this was interesting for marketing companies, right? We can test what people see and especially what they didn't see. Cool. And yes, there's Chinese on my slides. Anyway. So then we get to virtual and augmented reality. Of course, that's the main topic of today. So what do we do with eye tracking there? So virtual reality allows you to be transported to a new world of data or fantasy or whatever you like, right? And with augmented reality, we can overlay all kinds of very useful information, unlocking new levels of understanding that you otherwise wouldn't get with just your mortal eyes, right? But so how is eye tracking useful there? Well, this is, of course, this gets complex very quickly, and eye tracking is a useful tool for interaction, for instance. So goes back very far, actually. Eye tracking has been used a lot for helping people that are disabled, so they can't use their arms and such, to interact with screens. For instance, this guy is, that's not the kid's arm, that's the guy's arm, of course. He's eye typing here, so to say. That goes back 20, 30 years at least, that people already do this, so these technologies get better and better. But you can also imagine for you and me, why do we have to, if you're in a virtual world, why do you still have to reach for stuff? Maybe we just look at it and interact with it, right? Let's be even lazier. We don't have to get out of a chair and we don't have to move our arms anymore. How cool can it get? So, but eye tracking can be used, this is not really VR, but I want to just put the image out there as well. The future image of what can you do with eye tracking in the real world, ubiquitous computing, as Matthias was talking about as well. Well, we can use eye tracking for gaze contingent public displays, for instance, right? Where an advertisement actually reacts to how you look at it. You know, so the product follows you around, you can't escape it. Or gaze-aware warning systems. If you're driving your car and there's a kid crossing and you didn't look at it, then you probably want a very big flashing warning, right? Hey, look, kid, or just brake automatically. So that if a car knows what you're paying attention to, that could potentially save a lot of traffic accidents. Or just gaze-based interaction, any form of that. As you're walking around, your hands are full. It's nice if you can interact with your eyes instead. It applies to surgeons, it applies to you, trekking with a backpack and having a map in your hand and such, right? Cool, anyway, that's a nice future vision. So I cut some slides to keep this short. So opportunities for VR, eye tracking in VR. One thing you can do is to make VR more social. We can use character animation. So this is a little video from Toby. So there's a person looking in the mirror. Oh shit, this doesn't look very right. Anyway, you can see this avatar here looks pretty dead, right? Because it's not eye tracking enabled. But then when she looks over here, now the avatar's eyes are animated based on the data from the eye tracker. So you can look around, you can blink and wink at people, right? So you can, and we all know that this little bit of social, this eye contact, this little bit of social information goes a very long way to really feel like you're together, right? So that is a simple manipulation, but it's a big step, I think, for, well, of course, Facebook is very interested in that, right? Having people really virtually meet. Then opportunities for AR, well, there's all kinds of collaboration that you can do. Like, let's not forget that both VR and AR are not single user experiences, right? The real power comes out when they're multi-user experiences. So you might have a few architects, or what are they? Mechanical engineers, probably, actually, talking about some interesting engine block, I don't know. Interacting with each other, right? But it can be really helpful if you can see what the speaker is currently looking at. If you have a little dot saying that's what he's talking about, right? If you have a very complicated display, lots of things to distract you, having this little bit of extra information can really help you focus and cut through the distraction, so to say. So it's a cool opportunity for eye tracking in AR. Let's see. This just got real, right? Actually, things are getting nicer and nicer. So what can you do with us, I would say? I'm here, of course, selling you the Humanities Lab a little bit, as we always do when we talk. Anyway, so this is our current digital classroom and my kit. He's not included. But the tables move automatically. He had a lot of fun with that. But anyway, so basically it looks like normal screens and a lot of mess on the floor. It's cleaned up now. But what's interesting is a little box below the screen here. So that's the eye tracker attached, measuring what people are looking at on the screen. And we want to use this to measure see what can we, if we have a digital classroom of the future where you have eye trackers built in, how can we enhance education with that both? How can we help the teacher teach better? How can we help the students understand better? So there's a few examples of a little project that we're trying to develop together with Matthias in the educational science department, where you can think of multiple stages of teacher support and teacher training. So in the first step, teachers nowadays actually have very little experience in front of a classroom once they graduate. It's 20 hours or so. So why not build a VR environment where you have a VR classroom and you can get all the experience that you want. You can train the same scenarios over and over again, very rare scenarios that you won't normally see in a classroom only once a year or so. You can train those many times beforehand already. And VR, of course, gives you new abilities, right? You're in this virtual space where you're a kind of god, so you can just pause and see what's going on around you, right? See it from a different perspective, from a student's perspective. What do I actually look like? And using eye tracking, you can see, do I make the right kind of eye contact? Did I just simply not look at this information over here, the student that's disruptive that I really should have looked at? So that's step one. Once you get a little bit of experience, you're going into a real classroom, something like this. Right, and now here your task is also find out which students are going to be disruptive and make sure you stop them before anything happens, right? So novice teachers, they look at things that are salient, attract attention, like a wobbly leg or so. That's not important. What's important here is this guy doesn't even have material on his desk, right? So he's going to be a problem later. He's going to get bored. He's going to cause trouble. So imagine now, if you have a HoloLens, if you're wearing a HoloLens and your teacher mentors in the back of the classroom and he can in real time just say a little cue, here's where you should be paying attention. You're ignoring that. Especially if you build an eye tracker, you can say, you never looked at this, right? So here's where you should pay attention. Just bam. Then this student in situ gets the training he needs instead of a discussion afterwards, and that situation might never occur again, right? So that really can enhance learning. And of course, after the fact, you have this recorded video of the class, GDPR notwithstanding, and with eye tracker information as well. So you won't have a discussion with your student. Yeah, I saw that. I chose to ignore it. You can say objectively, you didn't look at this, right? You need to change how you behave. And the third step is back to our digital classroom idea. Why do we have all these eye trackers? Well, it allows you to keep track of what students are up to, right? Their cognitive state, if you will, if I extend a bit beyond what you can really do. So it would allow you to figure out which students are on task and which are not, and which are having difficulty with specific words they're reading or so, which are not looking at this image that's really important. But then even if you have that information, how do you get it to the teacher? Right? The teacher is busy teaching. You cannot put an extra screen on their desk and say, hey, student 17, there's an issue there, right? You don't have time to look at that, and even if you do, who the hell is student 17? So what you can do instead, we're thinking, is something like this. Just put little Sims icons above their head. If it's green, it's good. If it's red, it's bad, right? And then, of course, you can interact with the icon to get more information about what's actually bad. But, and even during this, I would say this is something useful, potentially useful for even very experienced teachers. It's always hard to read from bored student faces what they're actually up to, right? And again, this recording people, their lecture and what they're looking at helps also experienced teachers discuss with other experienced teachers about, hey, how would you approach this situation, right? What did I do wrong? Because you can check what you did and such. Anyway, that's it.